All right, I think we are ready to do our first example using Stokes Theorem. So we're looking at exercise 1 on page 160. And so here we have given a vector field f, and we have a surface S that is a portion of a paraboloid given by the equation z equals 9 minus x squared minus y squared that lies above the xy plane oriented upward. So we have all these pieces that are given to us, and they are asking us to calculate the flux integral through S of the curl of f dotted with dA. Okay, so they ask us to compute a flux integral. I asked you, well, actually the lesson plan, we asked you to draw the surface and the boundary curve. And I hope you had a chance to do that, because this is definitely the first thing that we need to do. We need to get a feeling for what does the surface even look like. So it's a paraboloid. Let me draw my 3D axes right here. We have 3D axes. We have x over here, y over here, z over here. And we have a paraboloid that's upside down because it's 9 minus x squared minus y squared. And we can see that when x and y are 0, z is equal to 9. So the vertex is up here when z is equal to 9. And then we have this upside down bowl. So that intersects the xy plane in a circle. So I'm going to draw in my circle first. My circle is going to go somewhat like this. And then I have my paraboloid coming down. Well, that doesn't look that great, but good enough. So this is my surface S right here. And then we can draw in the boundary curve. So just with the bowl that you saw in the previous two examples, the boundary curve is the lip right here. So I'm going to draw that in. That is my boundary curve C. Now the question is, what are the orientations associated to the surface and to the curve? They say that S is oriented upward. So I'm going to use this third color. S is oriented upward. So that means my normal vector points that way. This is my normal vector. And so when I apply the right hand rule, I would be curling around this way. And so the orientation on C is pointing from our point of view to the right. Okay, so this is what we have. So we now have our problem nicely set up. I hope this agrees with what you had. And so now we can look if we can figure out how to compute this flux integral of the curl of f dA. And so we have this surface, we have the curl of f. That would be a little bit of a pain to compute. You can see the curl right here. We have, that would be lots of partial derivatives to take. So now we have Stokes theorem though, and Stokes theorem says that in a situation like this, you can replace the flux integral of the curl with a line integral of the boundary curve of just the vector field dotted with dr. And we have a very nice boundary. So C is nice. So notice that C is pretty nice. It's a circle. And it's a circle of, we didn't draw in the radius, but you can imagine right here, the radius is going to be 3. We're going to double check that, but it makes sense. You have 9 minus x squared minus y squared. So when z is equal to 0, you have this 9 right here. So this is a circle of radius 3. And so we just have a circle of radius 3. And it's in the xy plane. That's pretty nice. So this is a nice easy curve that we have parameterized before we can deal with that. So our boundary curve really let's just confirm. So we have z is equal to 9 minus x squared minus y squared together intersected with z equals 0. That together gives 9 minus x squared minus y squared is equal to 0. And that, just to confirm, is x squared plus y squared equal to 9. That is our circle of radius 3. And so we can parameterize it. And we can parameterize it. X is equal to something, y is equal to something, and z is equal to something. Now it's in the xy plane, the circle, so z is going to be equal to 0. And then you can show that we have radius 3, so if we get 3 as our radius, and we have cosine t, sine t, you can convince yourselves that the orientation works. And so this parameterization gives us our vector r of t, which is 3 cosine ti plus 3 sine t j plus 0k. And t goes, well, we have to go once around the circle, so we have 0 less or equal to t less or equal to 2 pi. We are most of the way. We can set up our integral now. So now we can compute our integral. Okay, we want our surface integral, but instead of doing the surface integral, but I'm going to write it down anyway, curl of f dA. But instead we are computing our line integral over C of just our vector field, dr, and that we can do that because of Stokes theorem. That's the application of Stokes theorem. And now we compute a line integral the way that we know how to compute line integrals. We have our integral of our vector field. Our vector field is x squared zi. It's off the page, but hopefully you're following along. Y squared e to the x zj plus z squared e to the y k. So that was just our vector field. And then we are dotting that with r prime of t dt. That's what our dr is. And the limits are our t limits. So from 0, t equals 0, to t equals 2 pi. So right now I'm still mixing x's, y's, z's, and t's. I need everything in terms of t. So looking at our parameterization, hopefully a few nice things happen. And the fact that z is equal to 0 is going to be nice, because that z right there is going to be 0, and this z right here is going to be 0, so I don't even have to bother with anything else. This z up here is also going to be equal to 0, so e to the 0 just gives me 1, and so lots of nice things are happening here. I get 0i. Then I have plus that y squared. I actually have to plug that in. So y is 3 sine t, and that squared. E to the whatever is just going to be, well, we have e to the 0. And then my k component is also going to be 0. So we have that. And we can go back to r and compute r prime. That gives us minus 3 sine t. So I'm right here. We can compute r prime of t real quick. So that's minus 3 sine t I plus 3 cosine tj plus 0k. Nothing to do there. And so that's where I'm right here. So I have minus 3 sine ti plus 3 sine t, oh, sorry, cosine tj plus 0k dt. So not that much is left after I take this dot product. Only I have the 3 sine t squared, and then I have 3 cosine t. Only the j components are going to give me something non-zero. So I have 3 squared and another 3, that's a total of 27. And then I have my sine squared t and a cosine t dt. Okay, now we could do a U-substitution, and I leave it to you to do the details right here, but you could let u be equal to sine t, and then when you go through with the U-substitution, you end up with 9 sine cubed of t. And we need to plug in 0 and 2 pi, so that you get with the U-substitution sine t, but then I leave the details up to you. And when we substitute 2 pi and 0 into our antiderivative, we have 9 sine cubed of 2 pi minus 9 sine cubed of 0, and all this work to get 0. Oh well. All right, so the moral of the story is our surface integral right here is going to be 0. How about that?